This video is going to discuss section 14.4 powers and roots of complex numbers in trig and exponential form. Now this first video is going to discuss powers of complex numbers. The second video will discuss roots. So if you look at a complex number in rectangular form and you see it to a power such as this, so say for instance we've got 3 plus I quantity to the fourth. Now that means we would have to do 3 plus I times 3 plus I times 3 plus I times 3 plus I. So we have it 4 times there. And that means that we would have to multiply all of these together. So if we were smart about it, we would group the first two and the second two together. We'd say, okay, 3 plus I quantity squared is going to give us 9 plus 6I plus I squared. Likewise for the second, 9 plus 6I plus I squared. Now remember that I squared is really -1. So we end up with 9 minus 1, which is 8, plus 6I times 8 plus 6I. And then we can multiply these together. We end up with 64 plus 96I plus 36I squared. Again, I squared is -1, so that makes that -36. We end up with 64 minus 36, so 28 plus 96I. So there's not a real easy way to get to this. You have to go through several steps, but you can get there. And again, this was only to the fourth power. If it had been cubed, we would have done it differently. If it had been anything higher, we'd have to do it differently. So this one actually didn't end up too bad, but they can get kind of cumbersome. And so that's why we look at how to multiply things using trig and exponential form. The first thing we're going to look at here is what is known as DeMoivre's theorem. Now, DeMoivre's theorem says that if you have a number in complex form in either trig or exponential form here, that you can, if you're in trig form here, what you're going to do is you're going to take your radius to the nth power and you are going to multiply it by cosine of n times theta plus I times the sine of n times theta. Now if you remember from multiplication, this kind of makes sense because we added the angles together when we multiplied complex numbers in trig form, and likewise we multiplied their radii. So this makes sense. You have the radius to the nth power and you have the angle multiplied by n. It's even easier to see with the exponential form. Again, you kind of distribute that. You get r to the n e to the I theta n. So let's try an example. First example here is in trig form. Our radius here is just 1 in this case, so we end up with 1 to the fourth times the cosine of 4 times 35 plus I times the sine of 4 times 35. And you can see here how this is going to be a case where we're really going to have to pay attention to this angle. Again, this is always going to be between 0 and either 360 or 0 and 2 pi. You can see when we're multiplying by these numbers how these angles could get rather large, and we're always going to make sure that we have to put them within the first rotation of the unit circle. So we've got 1 to the fourth is just 1. Then we end up with cosine 4 times 35 is 140, so we're okay. We don't have to convert that angle, plus I times the sine of 140. And again, this just asked for trig form. It didn't ask to go back to rectangular, but we know how to do that if necessary. So I want you to pause the video here and try example 31. So for this example, you would have, just by doing the math part of it, 3 to the fifth is 243, 5 times 150 is 750. Again, 750 is bigger than 360, so we need to subtract off 360. That gives us 390, which is still greater than 360, so we need to subtract again, and we end up with an angle of 30. So our final answer here is 243 and an angle of 30. Now let's take a look at an example in exponential form. Again, we're going to end up with 2 cubed and then e to the 4 times 3 times I. So we end up with 8 e to the 12i. Again, 12 is greater than 2 pi, which is approximately 6.28. So we need to subtract 2 pi. And we'll end up with approximately 5.72. So our final answer is 8e to the 5.72i. Now let's take a look at an example when we've got something in rectangular form already. So we can either do like we did before, FOIL and FOIL again, or distribute and distribute again, kind of square things and then square them again. Or we can convert it to complex form and then use DeMoivre's rule. So if we use our conversion, we end up with r is the square root of the square root of 3 squared plus, again, our coefficient in front of I is just 1, so that would be 1 squared. So we get the square root of 3 plus 1 is 4, or just 2. And then we want to take tan inverse of 1 to the square root of 3. If we do that, we end up with approximately, if we want to stay in degree, we would end up with 30 degrees. If we want to be in radian mode, that would be pi over 6. It's up to you, whichever you prefer. And then now we would take this to times the cosine of 30 degrees plus I sine of 30 degrees. And we would raise that whole thing to the 4th, so we end up with 2 to the 4th times cosine of 4 times 30 plus I times sine of 4 times 30. And that ends up being 16 times the quantity cosine of 120 degrees plus I times the sine of 120 degrees. Now, if we put this back in rectangular form, again, distribute 16 times the cosine of 120 is -8. 16 times the sine of 120 is approximately 13.9 I. So that's just another way of getting to the answer. Again, in this case, it's probably about the same amount of work as going through and foiling everything out. But if it was any higher exponent, this would be a preferable method for finding the power of the quantity square root of 3 plus I. This is also helpful when we're dealing with negative exponents. So suppose we have the square root of 3 plus I to the -2. And in this case, what this really means is we've got 1 over the square root of 3 plus I squared. Again, we just found what this was in trig form or polar form. So we could instead say that we've got 2 angle 30 degrees. Again, that's what we found, 2 angle 30 degrees. And we want to raise this to the -2 power. Well, again, we distribute. We've got 2 to the -2. Angle here is -2 times 30. So we end up with 1/4. 2 to the -2 would be 2 squared, and then flip it over the fraction bar. And then our angle here is -60. Again, we don't like angles that are negative. We would need them to be between 0 and 360. So we would just add 360 to this. We end up with 1/4 times the angle of 300 degrees. Again, if you add 360 to that -60 degrees. So this concludes the video for the first part of section 14.4. The next video will discuss how to find roots of complex numbers using DeMoivre's theorem for roots.